For myself, if you have not met me, I am Shivani. I'm one of the simulation specialists out of our Texas region, and I've been working with flow simulation for 8 years at this point. Got a chance to work with many customers in our region and see many of the different types of analyses that they do. I consider myself very lucky to have seen those various cases. I will do my best to help you with any questions that you may have. You get to play Stump the Chump. If I don't know the answer, hey, I'll write your name down. We'll talk to the developers of Flow and get back to you. Okay. Other than that, let's go ahead and get started. So there's kind of some options for you. So for option number 1, I've kind of listed out our common questions that I get asked before somebody owns flow simulation, after they own flow simulation, and then some various vignettes of functionality within the program, things that I think are less used but could be interesting to some of you. Again, these are just options. So what I'm going to do is put up a timer for 1 minute, let you guys start typing into the chat and either voting on one of these 15 topics or typing in your own topic, and we're going to start from there. So because this is more of a loose type of webinar, it's not structured beginning to end. I want you guys to get what you came here for, get out of it what you came here for, so the more you put in, the more you get out, right? If you do choose to unmute yourself and ask questions, you get priority over anybody in the chat. So we'll work out whatever your question is. But we'll do a max 10 minutes on whatever the topic is, and then we'll take the rest offline at a later date. Okay, here we go. Let's go ahead and start this timer. And I'm going to start monitoring the chat, putting tallies in here for questions. Oh, I see you also here in the Q&A. That's perfect too. Perfect. Thank you guys. So we'll have time to do more of these votes after. That's the only time you're going to be able to vote. Anyway, the one that seemed to win, a lot of them got only 2 votes. So we're going to start with the ones that got the most votes here. So I'm going to do 9, we'll do 10, things like that. I've got my tallies here. So, absolutely 9 is the one I get asked the most often. I have this specific study. There's specific questions I have on it. I'm lost. How do I figure out if I set it up correctly? And because of how custom it is, really the best option is just to talk to me or another specialist one-on-one. Maybe you're not aware that you can do this, but you can schedule a session with a simulation specialist like myself. So I'll take you to our website real quick. This is, you can navigate to it through our services dropdown or our support dropdown, application mentoring session. And that's getting you to this link that I've pulled up right here. Now, if you're here and you're scrolling around, you're going to see that they each cost $250 for an hour. That's just to kind of put a wall between a random person who's not our customer being able to access this. Since you all were specially invited here and you are our customers, just reach out to the account manager that invited you, and they can get you either direct access to a simulation specialist or a coupon code for this to make it free. Point is that you are supplied this one-on-one session by being a customer of GoEngineer. I want to help you. So reach out to your account manager, get that coupon code or have them link you up with one of us, and we will do a one-on-one session with you and work out that custom model, okay? But that's really the best way to handle something like this. There's no artificial intelligence inside of Flow just yet that can kind of run a test for you to see if it worked out well. So one-on-one session's best way to go. So number 9. The other one that got 2 votes was number 10. So we've got, are my results accurate? So this is going to be a little bit of a longer little talking point. 4 or 5 things I want to walk through with you. So if that question gets asked, are my results accurate? The first thing that I do with the customer is check their assumptions. So, SOLIDWORKS. How to check the assumptions? Well, really you want to go top to bottom through what you set up in the project through till the bottom of your flow tree. So let's open up a project here. So first our general settings. So I'm going to right click on input data, go to my general settings, and I'm going to walk through, or I would walk through these with the customer, figuring out what do they turn on, what does that mean, what fluids did they choose, what materials did they choose, and then writing down, okay, how many times are they using something default out of our library? What did they choose to ignore? Roughness 0 micrometer, right? What did they choose to ignore? What did they plug in? And helping them understand each of those assumptions in each choice. Like black body wall as a default choice. What does that mean? When you're doing this on your own, take advantage of the flow simulation help, okay? A lot of SOLIDWORKS functionality is going to have this little question mark at the top right of commands, and that can get you access to this help kind of direct access to whatever you're trying to reference. You can also go through the SOLIDWORKS help up here, SOLIDWORKS simulation, flow simulation help topics, right? You look up what you need to look up, you read through it, and that helps. Honestly, that's a great way to learn the program. What about this did I not understand? Okay, now I understand what they mean by black body wall, by what it means when it's a default, that type thing. Hey, not every answer is going to be in here. That's where GoEngineer comes back in. If you are not able to find the answer you want in the supplied technical information, shoot us an email. Again, you can reach out to your account manager or our support team has an email and a phone number available on our website. You can find that here. So you can call us, you can email us, and if we can't directly answer it through some extra information that we have access to, we'll contact the Flow developers, okay? And that's how to check your assumptions, figuring out what Flow is actually doing. I think those steps will get you very far. What's the next step? So after you check your assumptions, I mentioned, where am I? GoE support, okay, customizations. So what did you choose not to customize? What did you customize? If I'm concerned about what somebody customized, a custom fan, curves, let's say, a custom material, custom fluid, I'll take them back to default. One of the default choices that comes with the Flow database, make sure everything runs smoothly, and then we'll add one customization back in at a time and see how that affects results. That can help us figure out if there's an issue with one of the customizations. And again, if you put in something custom, a custom fluid, a custom material, of course, whatever you put in, you put junk in, you're going to get junk out, right? So we want to make sure we understand what we're putting in. That's where the help comes in. That's where GoE support comes in. Make sure you understand what data you're putting in, and then interpreting your results. So with that, I mean, are my results accurate? The best way to answer that is, well, you have to go through your assumptions and list them out. What do we understand? What do we not understand? If you don't understand something, you reach out to us. That's kind of the simple answer there. And then making sure the materials that you type in, the fluids you put in, are the defaults okay for what you need, or do you need to go put in something truly accurate to what you're analyzing? So putting in those customizations. The last thing, bullet point here I have is validation problems. So as you are getting used, if you're brand new to the program, Flow Simulation does come with a technical reference guide or an online tutorial guide, which can walk you through some standard setups. This can help with training, as well as proving out a concept. For example, how does fluid flow react behind a cylinder? Kind of matching up with hand calculations, comparing that to the fluid calculations and how to set that up. Understanding how to do it properly can help you understand how to set up your custom model properly. That's validation problems. Again, that's access to the help dropdown. Now, that's just some high-level answers. Some specific answers, depending on what you're trying to analyze out of Flow. This top right-hand corner, I can't show you the actual example because it's a customer example, but it is a thermal calculation with radiation, and they did an experimental test, and they tested with thermocouples on points of the model, and then we compare that against a flow simulation study. You can see the kind of range of this is a kind of standard accuracy I would expect a flow simulation trying to match a thermal analysis. So we're in that 1 to 3 degree range, okay? That's what I would expect to see from a thermal analysis. If you're not getting it, of course, we're here to help. Now, here in the bottom left-hand corner and at the bottom, this is more about lift and drag. We're talking about CFD, pressure effects, fluid flow effects like that are a question, but lift and drag is a very specific type of application. And it is very reliant on the type of turbulence model that you have. So what turbulence model does flow simulation use? When we're here in our general settings and we're getting to our last step, turbulence is kind of default chosen. It just says this turbulence intensity and length thing. Turbulent energy and dissipation. If you were going to search that through Google, that would be called the K epsilon turbulence model. K epsilon is a really good general use case. It's very stable. For lift and drag in particular, it's good for low to mid angles of attack. This has been tested against wind tunnel data, so you have some proof. This is flow simulation, by the way. So flow simulation, it's on a drone, tested in a wind tunnel. The coefficient of lift, our lift results, match very well from -10 to about 5 to 10 as an angle of attack. As you reach those higher angles of attack, where you have higher pressure gradients, we start to underestimate that lift. We start to lose track of the accuracy there. Something else I want you to notice, drag. Okay, so our drag results tend to have a pretty significant deviation. By that I mean they'll match pretty well in the very low angles of attack, maybe -5 to 5. They're pretty close. But as you get higher than that, you have a pretty big deviation. We're going to overestimate the amount of drag on the object. And that overestimation increases the higher the angle of attack becomes. Now, if you really were trying to, let's say you haven't bought Flow Simulation yet, but you're looking at it, if your purpose is to get really accurate lift and drag, have access to a different turbulence model. Don't go with Flow for the K-epsilon. K-epsilon is great for the low to mid angles of attack, right? You just saw that. But if you need something more specific, wider range of uses, we have other options for you, okay? That's not what this webinar is about, but know that we can help you. Okay, that's the Are My Results Accurate? I saw some questions pop up. Some custom stuff, environmental temperature, radiation, compressible, incompressible. Perfect. Okay, so that's not related to the Are Results Accurate. So let's go ahead and take a look at some of the custom questions that popped up, and then we'll get back into kind of standard stuff that I went through. All right, I'm going to just copy and paste some of these questions from our Q&A. Okay, thank you for holding on there. So let's start from the first custom question that came in. How do you model a pressure vessel being emptied? Okay, I'm going to show this to you from scratch. It's the basic concept is something called free surface, and that's a type of physics that we can turn on in Flow. And then the second kind of component to this is taking advantage of the transient piece and initial conditions. Okay, and then we're going to do a shell. Okay, simple pressure vessel. It's empty. Like so. So we kind of have two ways to look at this. Either we have the whole thing filled with a fluid like water, and then emptying at a specific flow rate at the bottom. We can define that flow rate. Or we just leave it as an open channel, open air, and it's kind of emptying like a bucket. Kind of two ways to handle that. If I was going to do the flow rate way, I would just have a opening like so. I would use a split line or some sort of lid or something to define where that outlet flow rate is. Kind of like that. So initially filled with water, what's the outlet flow rate? It'll empty. Now the special part is needing that free surface condition where there's air and water in the same chamber. So to finish up that, I'm going to create one more separate body. To be the initial fluid of water. Yeah, we'll just do this. I don't want to merge the results. And just to make this obvious what I'm doing, I'm going to shift this downwards just a little bit. I'm going to make it a little bit shorter so we have a little bit less water in the tank. Let's do 1 foot. The other way. Okay. All right. Now for the setup. So the setup, you go to Flow Simulation. I like to go through the wizard just because it's the easiest way to set things up, honestly. I've been doing it for so long, I still do it that way. Let's drop this to the desktop. Okay, so starting with the wizard, come on. We're going to go through our 8 steps. Really the big thing is turning on the correct physics. So at the physics choice, with my current way that I set this up, I would call this internal. I'm just going to drain out into invisible space. External, you could choose if you actually had a channel opening, a cutout at the bottom, and it was going to flow through, okay? But internal, for now, just going to flow outwards. For my physics, I need to turn on transient because it's going to happen over a period of time. Who knows what that period of time is? Neutron gravity for, of course, the liquid needs to fall down in the correct direction. All right, and last bit is free surface. This is what's going to allow you to have gas and liquid in the same chamber, air and water. Next. So as I get into this part where I'm choosing my fluids, you need to choose a gas and a liquid, or a gas and a non-Newtonian liquid. That's the mixtures that we can do, or liquid and non-Newtonian liquid. So those are the 3 combinations you can have. You make sure you've selected both. Kind of go through the rest of the wizard, doesn't matter as much this stuff. When you get to initial conditions, it's going to assume the air is the first thing, the gas is the initial fluid, and that makes sense. You want to leave it like that, you want it to finish, and right now it assumes just that little top gap area is air, and then this water thing is all solid, like metal or something like that. So that's not what we want. So then you come into something called initial conditions. You can set that up from your project tree. I tend to use this tree a lot just because it's what I'm used to. You could also come up here, and there's lots of stuff in the menu bar, right? So initial conditions. So I'll drop that in. I would pick that whole volume to be my water. I say disable solid components. That gets me access to all of the initial conditions that would be there for a fluid. So I'm not going to do velocity or anything like that. It's not traveling on a road. But I will say, hey, it's initially water. This is the initial pressure and temperature of the water. Turn on gravity effects due to the weight of the water, and good. That's great. Now, my initial conditions for this vessel are partially filled with water, partially filled with air. And as I run the study, I'm just resetting this. As I run the study, it could empty. Really, the last step at that point would be doing a boundary condition. Whatever your flow rate or pressure is at your outlet, you'd go put that in at the bottom or whatever. Okay? That is how you would set up a tank emptying. Environmental temperature is based on cloud cover. So you guys do a lot of solar analysis, or solar, yes, the sun's modeling, tracking across the object. Is there any sort of, what would you do for environmental temperature, right? Now, I wonder if you know about this. When you're in your general settings, and you're turning on solar radiation, what did I just do? Conduction, radiation, solar radiation. You have access to this kind of library of where the sun is depending on where you're looking at in the world. Some standard data is out there. I'm in Houston. I could choose Houston, for example. Time of day. And then you could put in this cloudiness aspect. So that's where flow simulation could help you guess how that's affecting your part file, okay? The cloudiness, the sun itself. If you're just trying to estimate what the temperature of that day is, that's really just kind of manual. You'll have to maybe just look at some average temperatures of that region. But if you want flow to help you, this would be the way. You would use the solar radiation aspect. Hope that helps with that piece. The third question there is the default fluid that we supply, whether it's air or whatever, is it compressible or incompressible? So it really depends on which fluid you choose. Of course, if you choose a gas, it's compressible. If you choose a liquid, it's incompressible, right? If you want your gases to react more realistically, instead of following the ideal gas equation, you have to use one of these real gases, okay? Or make your own real gas. You can see I've made a fake methane. Those ones will follow, of course, the more extreme physics. The regular gases just do the ideal gas equation. So the default fluid, whether it's incompressible or compressible, just depends on whether you pick gas or liquid. If it's low Mach speed, still pretty much considered incompressible. When it goes higher than Mach, it'll need the compressibility. So I'm looking at the questions while I'm answering. Let's look at these next ones in the list. And just type in more if I didn't answer your question correctly or ask to unmute, that's fine. So the next couple questions that came in have to do with contact resistance, when to use it. It seems to be built in certain scenarios. That's true. Let's go back to this model. Okay. So two resistor components are really, they're not factoring in the contact resistance between the chip and the board, okay? They're only factoring in the resistance inside the chip itself. Let's talk about what a two resistor component is. It could be a very complex shape, right? And we're simplifying this down into a simple rectangle with perfect touching faces and that whole shebang. So when we're creating a two resistor component, we're putting in that thermal transfer, which is a combination of the conductivity and any other contact resistance that's inside just that two resistor component, right? So this is just about what's inside the two resistor component. If you're putting it in manually, yeah, you could include the glue that goes between it and the PCB. You're just simplifying your use case, but you don't have to combine it here, okay? So two resistor components, it's just what's in the component. For when you should use contact resistances versus, this is actually a twofer, a two resistor or a contact resistance versus a thermal joint. Those are the two options you have for telling flow how a part file is interacting with the part nearby. Contact resistance or thermal joint. Contact resistance is meant for when part files are face to face, they are touching, they are coincident with each other. That's when you use contact resistance. And when should you use it? Pretty much anytime you have material data for what's in between two parts. I talked about that 1 to 3 degree accuracy on that thermal analysis we did. We made sure to put in contact resistance for all the big heat generating components. and big heat transfer components. As an example, do I have drawing tools? Let's leave that example to the side. So if the part files are touching and they are adding a lot of heat to the system or transferring a lot of heat to the system, I highly recommend you put contact resistance in. And again, they are meant for just the touching faces. Now, something I want you to notice here, at the bottom of these chips, I did not also click the face of the PCB, right? I just clicked the face on the 2 resistor component. Every face that you select in this tool, it's like it's being painted with the glue or the solder or whatever you put on. So don't select 2 faces between the components. By that I mean don't pick the 2 resistor component and the PCB, because now you're painting that resistance on twice. Okay? So just 1 face. Now, when should you use the other option? The one that I said was the other choice, thermal joint. If you look at that icon, it's 2 part files separated by a gap. So you should use thermal joint if you have 2 part files separated by a gap. It's going to pretend like there's a part file that you modeled in with whatever resistance or heat transfer that you supply. Okay, so thermal joint to represent a larger component you didn't model in, or a thin component you didn't model in, contact resistance for faces that are touching. I guess the second question, heat transfer from a bolted interface. Let's say there's a diameter of that bolt. How to best model the bolt and make it easier to mesh. Rectangles, circles, similar areas for the bolt, that type concept. Okay, so if I think about a bolt, they kind of remind me of a via, and a via on a circuit board. So kind of multiple pieces to this conversation. I'm going to start with the first piece. Let's just draw, well, that's not a rectangle. Let's draw a bolt on a side view going through some PCB stuff. Okay, maybe multiple layers, and then of course there's some part file down here, and then it's either threaded into the bottom or a washer or bolted into the part kind of thing. Okay, a via kind of acts pretty similarly where it connects between part and part. A simplified way to represent this without having to mesh it is using a thermal joint. Okay, so you consider this a side view. Now I'm going to draw a top view. Okay, keep changing the colors of things I don't want to change. So consider this a top view. This is looking down on my board. Nope. I would do a split line in the shape of the bolt, and it would be kind of the diameter of that metal component touching the PCB. Then on the bottom view, I would do the exact same thing, whatever that bolt is connected to. Great. Same thing on the bottom down here, as I did up here. So that's this, and then I'll do the same thing down here. Then with the thermal joint, I would connect this face to the bottom and tell it the conductivity of metal. That way you don't have to mesh the bolt. I've forced the conductivity of the metal here like this. So set again, top face of the bolt, bottom face of the bolt, but you don't actually have the bolt in there. Just top face of what the bolt covers, of what the bolt touches, bottom face of what the bolt touches, put in thermal conductivity of the bolt. You can now represent the heat transfer of that bolt without having to mesh it, okay? That's the easy way, or the fast way at least. Fast in terms of analysis time. If you really just want to leave your bolt in and you don't want to deal with split lines and thermal joints kind of thing, The second best recommendation is stick with simple geometry. Don't do threads. Flow simulation hates threads. It confuses it to no end. Please get rid of your threads. And then second bit, flow simulation meshes square shapes better than round shapes. Round shapes will end up needing more mesh to capture the geometry. So if you can represent your bolt as a square instead of a circle, it's going to mesh that easier and have a lower mesh count and thus faster solve time. Okay? So first recommendation, thermal joint. Second recommendation, square shapes if possible. Someone asked a question, relating back to the bad tank that I drew, with the water overlapping the edges of the tank, and is that going to be a problem? Come on. Here we go. In this case, no. It just matches the solid level exactly, so it's not going to try and inject water into the solid body at all. So that's fine that it's overlapping. Flow simulation is pretty cool with overlapping stuff in general. If I had had it sticking outside a little bit, that would have been the problem. It would have just flown off into space and been confused. So overlapping is okay in this case. And then another question, I think this is going back to the cloudiness question. Is the environmental temperature different to the ambient temperature somehow? So no, there's really only one place you can put in an environmental or ambient temperature, and that's here in your general settings. And you kind of put it in here. That's your environmental or your ambient temperature. And that's the same thing. I wonder if there's some other temperature you might be talking about. I'm just going to come here back and look at the solar study again. So I don't see a place I'd be overriding this. Maybe here, but that's the same thing. So I'm going to go with, I believe I understood your question. I believe you're talking about this area of the general settings, and the environmental temperature. This is treating this as the ambient temperature, the environmental temperature. All the air around the object, anything that blows in is going to be that temperature. I'm not sure if I answered that one, but I'll watch out for more questions related to that. Let's do a faster one, and then we'll get into these custom ones. We had a couple of votes for the vignettes. So a faster one, does it work with whatever imported file format? Okay, the most common ones I get asked are, is it going to work with some other CAD modeler that I have, other program that I have? And in that answer, usually the answer is, okay, you're going to have to import that as a step or an IGES file. The nice thing about Flow is it's just in the SOLIDWORKS interface. So whatever power that SOLIDWORKS has to import a file type, Flow Simulation can use it. It just has to be in the program. And so the question really is, can SOLIDWORKS import it? So if your question is, hey, can Flow use blank file type? Just see if SOLIDWORKS can bring it in. That's answer number one. Can SOLIDWORKS bring it in? Can you make a solid part out of it? So generally that's step and IGES. Step or parasolid is preferred. Now second, a lot of people are using Flow Simulation for electronic circuit boards, PCBs, that type thing. There are programs out there like Altium that have direct connections to SOLIDWORKS. And they can also export step. I've seen that in action, so that's always an option. But if you happen to have Altium, for example, there are these connectors called a PCB connector, where your geometry inside of Altium can connect to your geometry inside of SolidWorks. If somebody makes a change in one or the other program can be updated. So it's all like a live connection. But same thing, then you're kind of working with SolidWorks part files as well. Just another option for you for connecting that data. The last bit here, kind of the specifics of what is going on with the model itself inside of SolidWorks, kind of funky ways we can have part files. This one that I made here, this is called a multi-body part because it's a SolidWorks part file, but it has multiple solid bodies in it. Totally valid way you can absolutely run a flow simulation on this. Even if I didn't have the move face, if I just had one part file, I could still run flow simulation on it. An assembly, just like the LED bulb I've been showing, absolutely possible. So where does the problem come in? It's when you have surface bodies. So when you import a step commonly, well, maybe not commonly, but if you import a step file, you can have an issue where not all the geometry gets imported. Okay, no. So the step file brought in, but there's some errors. You can see that here on the left-hand side. Let's kind of focus in on what's going on here. I've got solid bodies, which is that piece. That imported properly. It's a 3D solid. It has volume. I could technically run flow simulation on this. Now the other pieces, they broke during the import, and they're surface bodies. I know that because they're under the surface bodies folder. I also know that if I isolated one of these components or bodies, they're not going to have any thickness. They've got these blue edges by default, no thickness. Flow simulation has no idea what to do with a part that has no volume, and so it's going to completely ignore it. It can't mesh it. It can't do anything with it. Can't handle it. So if you're importing geometry and you see this kind of stuff happen, you are going to have to go back to your SolidWorks CAD modeling book or whoever you work with at the company that can help you out with that to turn it back into a solid part, okay? What are good ways to learn the software? That's a different version of this question, number 3, and that's kind of what I was leading towards with this one. So let's focus on how would we learn this. Let's start with what's available to you right now that's free, that you don't have to pay for. Okay, so starting with tutorials. So we had talked this before. You go to your help at the top right, SolidWorks Sim online tutorial, and that's a very long PDF with 15 to 20 examples. The part files come pre-downloaded on your computer. You can walk through them, get a baseline understanding of flow through this. It's plenty to read as well, right? They're going to kind of explain why they're doing what they're doing plenty of times throughout the process. Background info. So that's piece number 1. I will say that when I first learned SolidWorks, I was going through tutorials, and it didn't help me that much just because it was so perfect. Perfect little examples that I followed instructions, but it didn't help me understand, okay, what do I do when I have this custom situation come up? And that's where Crash Course comes in. Let me not forget my.solidworks. So my.solidworks is SolidWorks' database of free training material. It was the SolidWorks forums, which are now accessible through a different portal, but
They are here as well, where you can ask the community questions. It's another free resource, right? To get access to more information, I recommend you create a login. You can have a login for free. It doesn't cost you anything. There are different levels. You could pay for higher levels, that is true. But you can certainly have access to the free stuff with a login. Now what you would do is you'd go to training. You'd search Flow Simulation. And I can see I've got 10 lessons and 1 learning path to teach that program to me. And let's go to the learning path. The e-course costs money, so let's go to the learning path. All right. And this is made up of 10 lessons. You could go top to bottom. Again, that's supplied to you as long as you have a login. It's got to have a login. You can watch them. That's about an hour and a half training. It's kind of a crash course. It's enough to get you dangerous with the program. Alternatively, you had saw that application mentoring session. We talked about that before. You can reach out to your account manager or to a simulation specialist like myself who you already know and schedule 1 to 2 hour sessions with us to go over your model, your custom model. So what we would do, generally how the way that works, the first hour is almost entirely just setup, running results, and talking through interpreting the results. That's all. It's 1 hour. We don't spend any time on meshing in 1 hour. There's not enough time. In a second hour, we could spend that all on meshing and all your meshing options and dealing with that. So in about 2 hours, you can have a crash course of how to set up your custom model, how do I customize the mesh, how do I interpret results, okay? Now, of course, there's always more from that. That's what's free, what you can get. But once you're past that 1 to 2 hours and you need to get more custom, that's when you can go with mentoring. Mentoring is paid. It's a $250 an hour, right? You can buy more than just the complimentary free hours, or you can get paid classroom or online training. Those come with a manual. All of our simulation specialists here at GoEngineer start with the manual. We go cover to cover, and then we dig deeper in other categories, but that's how we start learning. It's a great way. I recommend it to start learning yourself as well. So the manual, classroom, or online training can also be very helpful. For any of those choices, just reach out to your account manager if you have any questions. Reach out to our support line if you have any questions. We'll help guide you the correct way. Okay, so let's hit the tallies here. 6 and 7. Let's do our meshes. Let's talk about meshing. So first of all, how do I view the mesh? I want you to remember this before I go show it in the program. This option called Use CAD Geometry and what it can actually show us. If you uncheck this tool, just remember that. Uncheck Use CAD Geometry. Remember that, you'll be able to see what the mesh actually is doing around your part file, how it's actually seeing your part file. Let's go back here. My favorite way to explain this is through one of our training files. So I'm going to pop up this regulator valve. This is a valve. It has a perforated cylinder through the center that's going to kind of regulate the flow rates. And that perforated plate at the center has a kind of varying range of holes. And because of that, some of the holes don't get captured correctly when you do the default mesh. So how do I view that? Let's first do a section view so I can show you what that looks like. Okay. So lots of holes going on here, flows going through. I haven't run this project. I don't need to do that to view the mesh. All I do is right-click mesh and I say create mesh, and that generates the mesh file. with whatever settings I have by default. Now that I've generated it, how do I look at it? Well, I want to make sure the mesh is good through this component. In my results area, I've got two ways that I can look at that. I've got this mesh area and I've got cut plots. Let's start with mesh. Insert. This one has a requirement of you've got to select surfaces. So I have to select a surface of my model like this. I cannot go through and select some standard plane like a front plane. Just can't do it. I can only do surfaces of the model. I'll go ahead and hit OK. I need to load in my mesh. And show you what I just generated. Okay, let's try this again. Insert. On my surface. Okay. A little bit choppy looking. Let's do a little bit of a cut plot or a section cut as well, crop region. That way I can see a little bit clearer what I'm looking at. So you can do this to your plots. You can always crop them to make them easier to understand. Okay, so what is this plot telling me? Well, if I'm looking at the way the holes look, they look pretty terrible. This is saying this is what the flow simulation solver sees. This is what the mesh looks like around those holes. It didn't get small enough to capture the small holes at all. Pretty chunky looking. There's also a gradient here, refinement level 1, 2, or 3. There was some automatic refinement that happened that just pulled up in my default settings. And so some areas are 2 times refined or 3 times refined. What does that even mean? We'll get to that. Now, what's the second way that I could view my results? Cut plots. This is the next most common way you're going to do it. You're going to pick a plane or a face. And this is the way you choose a plane, because in the other type, you can't do planes. And remember, this is that thing I told you to, please don't forget this part. Uncheck use CAD geometry. It's in your options. Uncheck that. That's going to tell you what the true mesh looks like. How flow simulation is actually seeing the part file. Let's focus on this area. That's definitely a funky geometry. I'll hide some stuff. Okay, look at that a little bit closer. It's not terrible, right? But you can see the chunkiness around that kind of smooth, curved geometry. And so that's another clue that that geometry didn't get captured well. And so then my next step would be refining the mesh in some of these areas. So getting into how to refine it. Because that's really the 2 ways to view it, and that really handles that first question. So how do I then refine it? Let's go through some vocabulary first. Okay, basic level vocabulary. A mesh inside of FlowSim is a big cube. Level 1 or level 0, just some big old cube around the object. You can kind of see that here in this picture. When you go to level 1 or 2 or whatever, it carves that cube up into 8 smaller cubes. Just divides it in half a couple times. You get 8 smaller cubes. So very quickly, you can blow up your mesh size. So we don't want to throw this all the way up to 9 immediately, pretty much ever. We want to be careful with what we're doing. So that's basic level vocabulary there. So let's take that knowledge into making the mesh better for this little piece down here. Okay. Meshing. So I'm going to right click on mesh and go to insert local mesh. Here you have two options. You have this first icon, which is telling me I can select components, faces, edges, or even a single point to apply all these settings to. Then I've got this one, which is you create a Boolean shape around your geometry, either a cube or a cylinder or something, and then again set up all your settings inside that Boolean shape. Okay. With this model, we pre-modeled in a little part file that just encloses the holes over here. So I'm going to go and pre-select that to just be looking at this area. Okay, and like I did say, this does take an hour to talk through all these different choices. So I'm going to give you the high-level answer. High-level answer, you're brand new to remeshing in Flow. What do I pick? Stick with these top two choices. Fluid cells or fluid solid boundary. They are what they sound like. I bet if I quizzed you right now, you'd all be able to guess what it means. A fluid cell is a cell that only touches the liquid or the gas or whatever. A partial cell touches both. It crosses the boundary, partially solid, partially fluid. And then you can't have full solid cells for doing like a heat transfer study where it's only in the solid. So when you're getting started, you're going to mess with these sliders. What do you think the numbers mean? They mean level 1, 2, 3, 4, 5, right? Just like we were talking about before. It's carving up that cube 1 time smaller, 2 times smaller, 3 times smaller. How do I see what it looks like? Take advantage of display refinement level. You can get an idea of what it's going to do. So looking at it like this, that's level 0, my default. We know the circles got down to level 3 with my default options. And so this is the type of cube that was around those circles trying to capture the curvature. No wonder it was so bad. What might be better? 4, probably even smaller than that. 5 is probably the biggest I could go to capture some of these smaller holes. Having decided that, I now have to go select that here. It's going to make it 5 times smaller. Okay, so that's you getting started. Now what's the downside to doing this one? Every single face, even the ones down here that don't really need it, are going to be 5 times smaller. And that can blow up your solve time, right? So that's where these other options come in and why they exist. These ones exist so you don't have to be so global, and you can really narrow down what you want. The place I go most often is advanced refinement. And yeah, there are a bunch of options here that look intimidating, but they really aren't too bad. The flow help does explain them with pictures and examples. You can see that here. So small solids, what is it? Curvature, what is it? How does it apply? Tolerance level, what is it? I'm here to give you the high-level summary. The high-level summary is tolerance is your best global choice. It's the one that's going to handle it the easiest, so you don't have to be as particular with curvature or small solids, okay? So tolerance, you don't have to be as particular. It's the one I recommend. Followed by curvature level. So tolerance first, followed by curvature level. The way tolerance works, if it notices that there's a very big difference in the shape of the geometry versus the mesh, it'll refine it. And whatever that error is, we are defining what it's allowed to change. So let's say the error is whatever. It's going to compare it against this number. If the error is greater than that, it'll refine the mesh. If it's less than that, it won't. Okay. So what I would do, I would set up at least a refinement level up to 5, and then I would give it an error that made sense for the size of some of these holes here. Let's start with the default. Hit OK. And then I'd remesh and I'd recompare. Okay. I'll go ahead and give that a mesh, but while it does that, I want to look at the questions again. Feel free to type anything in. We can go back to that. Otherwise, after this, we'll get into some of the other vignettes that you guys had requested. Do I know if SOLIDWORKS Flow will incorporate fluid structure interaction at some point in the future? It's a fantastic question. I am fairly sure they are not going to do it because of that other program that is going to be able to do it, that other thing that we offer. How do I show this again? Let's go to our website. Okay. So there's kind of two CFD tools in the SOLIDWORKS line. The one we're focusing on today is that SOLIDWORKS Flow, which, yeah, it doesn't have fluid structure interaction, which is very unfortunate. It's such a thing we asked for. But also in the SOLIDWORKS line is something called 3D Experience. And this does have a CFD tool in Abacus, which will have fluid structure interaction at some point this year, we believe, latest next year. So that functionality is coming to SOLIDWORKS users. It just won't be inside of Flow Simulation. I hope that answers your question, Edward. All right. So this mesh finished. So we're just going to hop back in here and see the changes. And then we'll go on to the vignettes. Okay. So there's, again, this is based on that tolerance level, right? Now it's going 1 to 5. So 1 refinement to some 5 over here. Yeah, it did a better job just with that tolerance level. Maybe I need to reduce the tolerance or increase the tolerance a little bit so that some of these holes that didn't get captured still get captured. And maybe go from 5 to maybe 6 or 7 because some of those holes didn't really get captured still. And that's the process. It's trial and error. It's back and forth like that, and viewing your results, viewing your mesh. Okay, so the first thing you have to choose when you're doing radiation is in your general settings. You turn it on. Let's just say we did with standard radiation, no solar radiation for now. You're only going to have one choice unless you paid for the higher choice. So you're going to have discrete transfer. Discrete transfer is great for the one that I said was 1 to 3 degrees difference. They use discrete transfer. It's great for most use cases. If you need to handle radiation through glass, like a greenhouse effect, where the glass is absorbing some of the heat but transferring some of the heat, that's where you need to pay for the extra level package, where you get discrete ordnance. Most people can stick here in discrete transfer. Okay, now as you're going through your wizard, the first thing you're going to have to choose is what's your default wall radiative surface. And in this case, I chose black body wall. But my recommendation, where'd it go? My recommendation is to use a non-radiating surface, actually. It does not take part in the radiation calculation. Come on. Why do I choose this? Well, what is a black body wall? It's basically a black hole. It's kind of extreme. You might hear people say, well, yeah, it'll get the worst case answer, which is true. It will get you the worst case answer. But it could also tell you your part's going to fail because it's too hot, when in reality it's not going to fail, right? And now you just spend extra 6 months redesigning your assembly for an inaccurate result. So I recommend you go to non-radiating surface. so that part files that aren't generating a lot of heat, are really tiny, that don't matter so much, hey, they're not getting factored in. It's a faster solve time. It's more realistic. So first of all, I would choose that. But this is going to put a lot of work into your setup after this, but that's necessary for accuracy, right? So non-radiating surface, that's my first step. Second step, and final step, honestly, setting up all your radiative surfaces. So a radiative surface is essentially your emissivity from that face. The program does come with many defaults that you can pick from. Be careful. It seems like, oh, it's aluminum, ref aluminum, sure, I can use that on this part file. Why not? You need to be careful with what you're picking, especially in a case where this is sitting in an outside environment. This LED lamp is sitting outside as well as radiating internally, right? So it's radiating to the outside temperature and the inside temperature. Come on, pop up. Okay, let's look at some properties here. In radiative surface type, there is a definition and it says wall. Wall assumes any ray leaving the surface of this LED is going to hit some other component and get absorbed by the other component. If there's a ray coming off this thing and it doesn't hit anything, it assumes it gets reabsorbed back into this part. Does that make sense for something sitting outside? It doesn't, right? This LED is radiating out to the air and it's going to air. It's getting absorbed by the environment. So it doesn't make sense to set a wall radiative surface to something that's an outside surface. Okay? So what am I talking about? Let's go make a new radiative surface and look at your options. You have three. You have wall, wall to ambient, or wall to environment wall. You don't really need to worry about environment wall. Wall to ambient or wall are the two choices you're going to be flipping between. Wall to ambient is what I just talked about. If it's your outside faces going to the outside environment, make sure you use a radiative surface that's defined as wall to ambient. Put in your emissivity. If it's an internal face, make sure your radiative surface that you apply to it is wall, right? So what's the workflow? I'm going to give you a SOLIDWORKS trick that I recommend. And it requires doing some setup on the part level side. Alrighty. So here, you would create something called selection sets. This is a SOLIDWORKS thing where you pre-select all the faces that you're going to want for something later, and then you save it as a selection set so you can get access to it very easy. The way it works, you control-click whatever you want. If it's a face that has a lot of tangencies like this, you can right-click and say select tangency. I can very quick select a bunch of stuff for you. Once you have those selections made, you can right-click and you say save selection, new selection set, okay? And you're able to build up these kind of pre-saved things. Of course, if you want to add to it, you just reselect it, click a few more faces, right-click, update. That easy, okay? So you build up your selection sets, and then back inside of your main flow project, when you're creating your radiative surfaces, you dig down through your tree, you find your selection set folder, you pick it. Now I selected external surfaces there, so that means that whatever predefined or user-defined choice I pick, it better be one that has ambient or wall to ambient properties, right? Wall to ambient properties. All right. that is essentially the workflow. And then you would do it again for the internal faces, but you'd set it for the wall ones. If you do that with your radiation, I am pretty confident you'll get very close to experimental results. You just got to be sure you have the right emissivity values. I'm always good at just talking forever, so I'm going to stop myself and explain what initial conditions are, because this is fantastic. Somebody had asked for this. This is fantastic for time savings. So initial condition, you saw a little bit of that with the tank. That's not what I'm talking about when I say time savings. So I'm going to stick with this example because I've been using it. We had a customer in this chat right now talking about solar studies. And if I was going to turn a solar study on for this LED lamp, let's say the sun started at 11 o'clock a.m., it tracked across the sky until 1 p.m. So the sun's moving across the sky. What does that sound like? A transient study. Transient studies inside of flow simulation are very time consuming. And I don't want to waste any time on analyzing 8 a.m. to 11 a.m. where this thing is just kind of chilling and heating itself up and kind of reaching a steady state. I don't want to waste time on that. So we make a combo version of this. Right now, what I have solved, the 6 watts total, it is a steady state. There's no transient going on. We get to kind of like a converged result of what it would look like if it's been on for a long period of time in a general temperature situation. Then, clone your study. Right-click clone. I'm going to call it my transient one. Fine. What was I thinking? Okay, then you're going to go to your general settings, turn it to transient, of course. Okay, now it's transient. Now here's the big thing. In initial and ambient conditions, where the transient starts at time equals 0, you can have that be equal to a different project. You would go to transferred, and you'd pick the flow simulation project you want to connect it to. Like my 6 watts total, that was my converged steady state result. Okay? It now ignores all of this stuff. It's ignored. It's using the defaults or the final answers of my initial project. And then it's going on with the rest of the transient analysis after that. So then you only have to run 11 to 1. You don't have to run 8 a.m. to 1 p.m., right? Big time savings. It works best for situations like this where you are trying to save time. So some sort of steady state connected to a transient state analysis. You guys have talked about emptying pressure vessels. Some free surface flow was a question here, and both are great reasons to take advantage of this trick. Get to a steady state answer very fast, or with a bad mesh, honestly. Get a bad mesh going, get to an answer, and then refine your mesh and import your initial results, right? Just any way you can import results, save yourself some time. Okay, and the last one that was requested was rotation and free surface. So let's hit that one at the end here. Kind of a workflow for that. By the way, this is brand new to 2021, so if you are using a version previous to that, you are not going to be able to do this type of physics. But 2021 is possible. I have a mixer here. This is a tank with some blades. that I'm going to set to rotate, okay? My setup is pretty similar to the tank filling or emptying that we looked at earlier. Let's look at those physics. So time dependency of X amount of time is going to be rotating. Gravity, of course, is necessary to keep the more viscous and heavy material lower. I set my sliding rotation. What does that mean? It's going to take those fan blades, it's going to physically move them in the fluid, pushing on the fluid. So it's physically moving the blades, pushing on the fluid. And then, of course, free surface is necessary for gas and liquid in the same chamber. So 4 sets of physics turned on here. Under fluids, I have air from my outside liquid, and I turned on applesauce. It's a default non-Newtonian liquid that we have. I went with applesauce. Yeah, just kind of partially filling this mixer bowl. On my initial and ambient conditions, I did a little bit of a trick where instead of pre-modeling in the applesauce volume, I said everything below a certain height is applesauce. So from 0 to -5 inches, it's applesauce. Just a little speed trick so you don't have to model it in. Having done that setup, there's not much else to do inside of this piece. There's this little special thing I did that's hidden. So I modeled a little disc that goes around the fan, that kind of encloses the fan. Anything this disc encloses is going to be treated as spinning at RPM. Anything it touches. You can't override any face. So if you have other faces sticking into this region that aren't supposed to rotate, adjust that rotated object, just that shape. In a lot of examples you see online from GoEngineer, we're using discs, like cylindrical discs like this, just because it's simple to model. You do not have to use a cylinder. It just has to be axisymmetrical, okay? It just has to be axisymmetrical. From there, I believe I just set up a RPM. I had it spin up from 0 and then stay at about 250 RPM. What does the results look like? This is called Transient Explorer, by the way. It saves a bunch of little iterations throughout the course of the analysis. So you can kind of see that spin up and move that fluid.
Can you hear me?
Yeah, I can hear you now.
Oh, perfect. So my situation is I make my upstream pressure time dependent variable, so I inputted all of my pressures from an Excel sheet.
Okay.
And then my environmental pressure is the downstream pressure. That stays constant throughout. And then through my simulation, after the simulation is running, my goal plots show the mass flow being negative and the velocity being negative.
Okay.
Of that fluid.
Okay, so something funky is happening where it's flowing backwards out through this inlet instead of going the correct direction.
Yeah, but when I do the flow trajectory and with playing that animation, the arrows are going in the right direction. It's just the crafts are dipping down.
Okay.
And it's staying constant.
Well, the mass flow rate I would expect to change as the pressure drops change. I wouldn't expect it to go negative. The pressures do allow any sort of directional movement. I guess the first thing I would look at in your case is I would do a surface plot on a face like this, on the inlet or outlet, and I would plot velocity in a direction, like in a y direction in this case, so I could see if majority of the flow is moving in the way I expect, and just some of it's curling back or something. So that's the first thing I would do. So I would do like velocity and y, and then when I get my results, I would do like -1 to 1, for example. So it's a really clear delineation between red and blue, and then I would just see how much of it is actually positive versus negative. And potentially do that on multiple cross sections. I guess I did it on this face. I would start there, but I would probably also do it on the front plane too, so I could just see if it's like a channel flow that's going the correct direction. Everything is cycling back in a weird way. I'd look at stuff like that, like kind of like a backflow situation might be happening.
Okay.
So yeah, that's the first thing I'd look at. That's the plots I would use to help figure out what's going on. That's the first thing I would do. Kind of the second things I might do concentric rings, or a grid pattern of some sort on the inlet and outlet face. That way I could get mass flow rates for individual areas. It could be another way to figure out, is it more of a positive versus negative?
Okay. What's the main difference between the surface goal and the global goal?
Cool. So a global goal is factoring in every face or point in space.
Okay.
Where a surface goal is, of course, just on a particular surface.
All right, understood.
Cool. Yeah, if you continue to have any more trouble, again, just reach out to whoever invited you to this webinar. We can certainly do a one-on-one. Okay, cool. Guys, if there's no other questions, we'll probably end the session. This is the first kind of roundtable style simulation webinar we've done. If you have any feedback from me or for recommendations, anything like that, if you could reach out to the account manager that invited you, that'd be super helpful. Otherwise, we'll send out an email with this in video form. What am I saying? We'll send a recording of this, of course, later. You can always reply back to me in that case. And yeah, any tips you could give me or recommendations, or if you have any other further questions, feel free to reach out. Thanks everybody for coming.